octet rule Lewis diagram, and we have already finished the first two parts, and now we consider the next one is about the molecular shape and the VSEPR moment. So first one we should consider what does it mean the molecular shape, and how can we determine the molecular shape. First one, we know that the molecular shape is a three-dimensional arrangement of atoms, which consists, the three-dimensional arrangement of atoms consisting of molecules. And molecular shape can be only experimentally determined by spectroscopic method. It means that we can determine the molecular shape only by the experiment. We cannot determine by the logical thinking. So this one is from the experiment. However, for some small and molecules and also the main group molecules, we can use the special theories or special models to predict the molecular shape. Okay, and in this case, the theories used is which the name is a valence shell electron pair repulsion. Okay, so this one is a shorthand of the this phrase valence shell VS. Okay, for valence shell electron pair EP, and repulsion is RE. So the name of this one is show us the principle of the theory or the principle of the model. And this one is very simple model, however, it is very useful to predict the shape of the smaller molecules of the main group element. Okay, so let's consider the principle or the assumption in the theories in the VS EPR mode, in the VS, in the VSEF, in the VSEF theories. So according to the VSEF theories, because you know that in the molecules, there are not only there are electron pair. This one can be the bonding or non-bonding electron pair. And because the electron pair is negative charge, so there is a repulsion between the electron pair. And now, according to the modern here, so the valence electron pair or the electron pair in the molecules will arrange how to minimize the repulsion between them. It means that so the valence electron pair arranged to minimize the repulsion between them. For example, we can consider yes, in case if in your molecules there are two bonding pair. So this one is two. This one is the central atoms with the red colors, and the smaller one is for another atoms or for another group which bond to the central atoms. Because here there are two electron pair. So now, in case of two electron pair, if you want to minimize the repulsion between the two electron pair, so the orientation of this two electrons is in the opposite way. So this one is direct on to the right, and this one is direct to the left. So it's one that they they oriented in the two opposite directions. In this case, we can obtain the linear geometries or linear shape. Okay. So this one is what does it mean? The distribution of the items in the three-dimensional space, or in the or we can call this one is a three-dimensional arrangement of the items. In this case, with the two electron pair, we can observe the linear geometries, and with the standard bond angle here is 180 degrees. Okay, so now let's increase the electron pair from 3 or 2. So in case of two electron pair, 1, 2, and 3, so the 3 one is arranged to the triangles, in the triangles. You can see this one is in the corner of the triangles, And now this angle is 120 degrees. Yes, this one is the standard bond angles, and this one is a molecular shape. In case of three electron pair, we can call it a triangle or the trigonal planar shape or the trigonal planar geometries. And for electron pair, it's not square. The geometry is not square. Instead of square and tetrahedrons, it's tetrahedron geometries with the bond angle is 109 degrees. Okay, 1, 2, 3, and 4. And when the number of electrons increase to 5, it's a triangle by pyramids. So the triangle okay, so in case of the 5 electrons, yes, yeah, this one is a form of 5 uh, electron pair, so the geometry is a trigonal bit bipyramidals. What does it mean what does it mean the trigonal bipyramidals? Because trigonal because here you can see so this three item is from the triangles, okay? In the same plant. And we have the first a trigonal pyramidal here. Uh, you can see here this one is a shape base between the two triangle pyramidal. That's why we call it a triangle bipyramidal. It means that it's two pyramidals. The first one is upper and then another one is lower. Yes. And for the with the 6 electron pair, the molecular shape, 6 electron pair, the molecular shape is for the 6 electron pair, the molecular shape is octahedron. You see, it's octahedron. Octahedron, yes, it's octahedron. It's not a triangle. Uh, it's not a tetragonal bipyramidal. This one is the name is octahedron. It's octahedron. Okay, so this one is a basic. This one is a basic geometry for the electron pair, for the number of electron pair from 2 to 6. 2 is linear, 3 is trigonal planar, 4 is tetrahedron, 5 is trigonal bipyramidal, and 6 is octahedron. And just please remember this, that this one has already learned in the fundamental chemistry one. Okay, so now let's consider assimilate more detail about the VSEPR, the VSEF theories. In case of the central atom has lone or bonding pair, uh, so in this case we must consider the order of the electron repulsion. So you can see the decrease in the sequence. So the first one is a lone pair, is the repulsion with a lone pair, the lone pair. In this case, please remember that in case of the lone pair occupy more space and more active than the bonding pair, because the bonding pair is and because in case for the bonding pair is between two nucleus, between nuclei. So this case is less reactive and occupy less space than the lone pair. So the lone pair is only belong to one nucleus, belong to only one nucleus. Okay, in this case, you can see that the lone pair is more active and more occupy more space than the bonding pair. Is why the repulsion between the lone pair is strongest, and then the weakest one is between bonding pair and the bonding pair, and in the middle is between the lone pair and the bonding pair. Okay, and now let's see the molecular shape in detail when we consider the bonding pair and the non-bonding pair. The first one is for the electron pair with the 2 electron pair. Okay, follow the two
Huyền ơi,
electron pair here.
thầy chưa chưa chuyển slide ạ.
Sorry.
Thầy chưa chuyển slide.
So let's see why this happened with this class.
Nó vẫn ở valence shell electron pair repulsion.
Who is the host for this video, for this videos? Who is the first one to enter the class?
Em thấy thì là hình như là Phạm Ngọc Minh rồi.
Em thấy là bạn Nương vào lớp đầu tiên ạ, nhưng mà mạng nhà bạn ấy hơi lag. Có thể sao vào lại.
Em vào đầu tiên nhưng mà nãy mạng nhà em nó bị chập chờn nên xong rồi em phải vào lại rồi.
I don't understand what's happening. Okay, anyway. Because with this one, which you can, when I choose this option, I could not draw anything on the lecture. Okay, so anyway, I don't understand what's happened here. And now here you can see the movement of the slides. However, I cannot draw this one anymore on the slide. So okay, we don't have any other option for this one. Okay, so let's consider the molecular shape. In case of electron pair, 2 electron pairs, so with the bonding pair is 2, and there is no way for the non-bonding pair. In case of this one, two electron pair, 1 bonding pair, and 1 non-bonding pair, it's easy to realize. So the molecular shape is linear. So here we consider the problem is a 2 electron pair and 2 bonding pair and 0 non-bonding pair. And this case, because of 2 electron pairs, so the molecular shape is linear. I think this is no problem for the first situation. And the situation with the electron pair is 3. So there are 3 bonding pair and no bonding pair here. So the molecular shape is trigonal planar. You can see it like this one. It's similar in the previous slide. However, let's consider the situation when there is 1 non-bonding pair and 2 bonding pair. And now you can see here there are 1, 2, and 3 electron pair. However, one of them is non-bonding pair and the remaining is bonding pair. But because this one, so you can see that this position is empty. So what happens when this position is empty? The electron pair has no shape. So it's this one, I mean that this one is the position is empty. So this position is empty. It means that now we can image that. So there is only 3 atoms here. In this case, they form the V-shape. The V-shape or the bench structures. Okay, so please remember that. So the molecular shape will depend on the non-bonding pair and the bonding pair. That's why we must consider the number of the bonding pair and also the bonding pair. In case of 3 bonding pair, the molecular shape is trigonal planar. However, in case of bonding pair is 2 and one non-bonding pair, so the molecular shape is bent, not trigonal planar anymore. And this one is electronic geometry. This one is the distribution of the electron pair. It's not a molecular shape. Please be careful here. So Okay, so first one is 3 electron pair trigonal planar, and then you can draw the structures and you consider is there any non-bonding pair. If there is non-bonding pair, so we can ignore this one when you determine the molecular shape. Okay, so the next one is an example for the electron pair, the number of electron pair with 4 electron pair. So here with the 4 electron pair, the electronic geometry is the tetrahedron. All of them are tetrahedrons. However, now the molecular shape depends on the number of the non-bonding pair. With no non-bonding pair, so you have four. There are 4 bonds here. So there are 4 bonds. So this one, the molecular shape is tetrahedron. However, in case of one non-bonding pair, so one non-bonding pair here, so there are only three bonds, and this bond is adopts the trigonal pyramidal molecular shape. Yes. And when the number of non-bonding pair is 2, so you can see that there are only 3 atoms and the shape is bent. Okay, so it must depend on the number of the non-bonding pairs. For the next one is valence electron pair is 5. Okay, with the number of electron pair is 5, so we have a different situation. The non-bonding pair is 0, 1, 2, and 3. Okay, with a no non-bonding pair, so the shape is trigonal bipyramidal. Okay, you can see the difference in the positions with the red color and also with the green color like this. So there are 2 different positions. First one is an equatorial plane, and the second one is an axial positions. Axial is with the green color and the equatorial with the red colors. And now there is one non-bonding pair, so we can draw the non-bonding pair in the equatorial positions here. Okay, and now let's image there is no item of this positions, and now the shape is the seesaw. The seesaw. Okay, this one is the seesaw. When the non-bonding pair is increased to 2 non-bonding pairs, so add 1 more lone pair in the equatorial plane, and now the shape is only the T shape here, the T shape. Okay, this one is why I cannot use a pen anymore, so I cannot draw here, so you must image by yourself. I'm not really sure why. With this class, I could not use this option for the PowerPoint. Okay, so and in case of the 3 non-bonding pair, all of them are in the equatorial plane, and now you can see the shape is linear, so it's only linear now. Okay, and shift to the another one is for the electron pair of 6, with the basic molecular shape is octahedron. With the 1 non-bonding pair, so because here you can have a 6 equal positions, so you can keep the non-bonding pair whenever you want. Whenever you want, so you can keep down or up, left or right, in front or back. It depends on you. However, the molecular shape is a square pyramidal. That image we erase or we ignore this position here. So there is a square base here, and this one is the top of the square pyramidals. And for the 2 non-bonding pairs, so you know that now because here there is a repulsion between the non-bonding pair and non-bonding pair. So the best way is we keep the 2 non-bonding pair as far as possible. So in this case, we can keep this one in the opposite positions. And now the molecular shape is only square planets. But this one is very easy to infer from the basic geometries. We don't need to remember, okay, so this one is, for example, when you learn in the fundamental chemistry one, so okay, so this is some kind of notation, okay, X, okay. This one is very difficult for you to apply this one. You don't need to remember you don't need to learn the molecular shape by heart. This one you can check, you can infer the molecular shape is from the basic geometry. For example, let's start from octahedron, and you move 1 position, you move the second positions, and you can obtain the final molecular shape. Okay, so now we can consider some example here with the VSF model. You can consider the molecular shape for the following chemical species. And now I would like to shift to another now we can consider these kind of examples. First one, we can determine the shape of the NH3, sorry, CH4. First one, let's consider the molecular shape of CH4. Okay, so for the molecular shape of CH4, at first we can draw the Lewis structures. Okay, first one for the molecular formulas. Start from molecular formulas, we can draw the Lewis structures or the Lewis diagrams. And then from the Lewis diagrams, we can apply the BS-EPR moment to determine the molecular shape. Okay, so let's start from CH4. So now from CH4, we can easily draw the Lewis structure. So this one is from the previous class, so I don't want to stop anymore here. We become more familiar with this one. Okay, so first one is the molecular Lewis diagrams. This one is Lewis structure of the CH4. And now you can see that the surrounding the carbon atom here, they are 1, 2, 3, and 4. So we know that with the 4 electron pair. Okay, with the 4 electron pair, so the molecular shape is a tetrahedron. Okay, it's tetrahedron. The first one, please remember the basic shape. For 1, 2, 3, 4. Okay, 4. This one is tetrahedron. And another one here, so hydrogen, 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 and hydrogen. So this one is molecular shape of CH4, and the molecular shape is tetrahedron. Okay. Now let's consider the second example. It's about NH3. So for the NH3 molecular, so first one we draw the Lewis structures of this one, the nitrogen bond with 3 hydrogen. Okay, so this one is a Lewis structure of the harmonious of NH3. So do you think this one is a correct Lewis diagrams, or can we add anything into this formulas? Kimai. So this structure is the correct Lewis diagram of NH3, or should we add anything into these structures? Việt Khoa. Việt Khoa.
Yes, I'm here.
Okay, so this one is the correct answer. This one is correct Lewis diagrams, or should we add anything into this one to correct the Lewis structures here? This one is correct or incorrect structures?
I think it's incorrect because it lacks one pair of electrons.
In which items? Okay, so it lacks one electron pair. So should we add any electron pair to which items? How can we correct this Lewis diagrams?
Add the two dots right next to the nitrogen atoms.
Okay, so add one electron pair in the nitrogen. Okay, now this one is a correct Lewis diagrams. You can see that what's the difference between this molecules and another. Okay, now let's consider two examples. The first one, we can draw the structures like this. Okay, this one is a layer diagram, and another one, this one is incorrect one, and this one is correct one. And now we can apply the BS-EPR theories for both of the structures. The first one, for the first structure, you can see now for the nitrogen 1, 2, 3. So in case of 3 pairs surrounding the central atom, so what is the molecular shape of central atoms?
It is a trigonal planar.
Okay, this one is trigonal planar. So in this case, you can here draw like this. Trigonal planars. Okay, and now for the second structures, this one. Now let's consider structures. How many electron pairs surrounding the nitrogen atoms here? Lê Phúc Thịnh.
I think molecular shape is
No. I don't ask you for the molecular shape. I ask you how many electrons are there surrounding the nitrogen atoms.
5 electron around nitrogen atom.
How many electron pair? Not electrons. Electron pair. Electron pair.
3 electron pair.
Okay, let's count together. Okay, you can start the countings.
Yes.
Let's count. You, not me. The first one is 1.
1, 2, 3, and 4.
It's 4, not 3. Okay. So with the second structure here, 1, 2, 3, and 4. So what is the shape for the 4 electron pair? What is the basic shape for the cases of 4 electron pair?
Trigonal pyramidal.
No, the basic shape for 4 electron pair. What is? 3 is trigonal planar. So 4 is
Tetrahedral.
Tetrahedral, yes. Okay, this one is basic shape for the 4 electron pair is tetrahedral. So now, first one is nitrogen in the centers. Hydrogen, and lone pair. And now, what is the molecular shape? This one is a lone pair. So the lone pair means that there is no molecule here. Okay. So what is the molecular shape here?
Trigonal pyramidal.
This one is trigonal parameters, not tetrahedral anymore. Yeah, this one's trigonal parameters. Next example is SF4. Okay, SF4, so the sulfur atoms in the centers. Now, this one is correct or incorrect Lewis structures. Nguyễn Khánh Linh. Huyền Chi. Huyền Chi. Thảo Linh. Diệu Quỳnh. Okay, please. Khoa.
I think the sulfur lacks one pair of electrons.
Okay, so this one is like one pair of electrons now. So this one is Lewis structure of the SF4, and now let's consider so how many electron pairs are in the same sulfur items here.
There are 5 pairs.
Okay, so 5 pairs. So because those 5 pairs, so the basic molecular shift is this one is a triangle. Sorry, a trigonal bipyramidal here. So this one is sulfur in the center with 5 electron pairs. So one of them is a lone pair. So here's the lone pair. You can keep it on this. Crazy. So there is one lone pair. Okay. This one is a lone pair from sulfur. So another position, remaining position, you can draw the fluorine. And what is the molecular shape of this molecules? What is the shape of this molecules? What is the shape of this molecule? This one is not trigonal.
It is a seesaw.
You can see that this one, because this one is the non-bonding pair. The non-bonding pair means that there is no atoms here, so you can delete this one here, and now this one is molecular shape of the SF4. Okay, so it's one easy for you to understand what does it mean. A seesaw, if I rotate the molecule like this, please take a look on here. Okay, you can see now this one is a seesaw. Okay, I think that image is the seesaw. Okay. Okay, the molecular shape is seesaws. So I show you the step how you can determine the shape of the molecules. To be sure that you draw the correct Lewis structures, and then from Lewis structures you can use the VS EPR to infer the molecular shape of the particular chemical species. And then the last one is IF4 minus. Do you have an idea about this? NNs. Okay, now for the IF4 NNs. So who can help me to draw the Lewis structures and determine the shape of these NNs? The first question is the Lewis structures of IF4 NNs. Big Ngọc.
Dạ gọi em.
Nguyễn Thị Bích Ngọc. Okay. So what is Lewis structures List diagrams for the IF4 minus, for the IF4 enhance.
Y đập 7 nha, Y đập 7.
Diagonal
Sorry, I asked you for the Lewis structure first, not the shape.
2 2.
Please understand the questions. I asked you for the Lewis structures of IF4 minus of the IF4 enhance here. So what is the Lewis structures?
diagonal pyramidal.
It seems you don't understand my question, sorry. Okay. So next time I will ask faculty to check for your English before we start the course. This time of you and also of the lectures with this kind of English. So, Khoa. No. Quốc Đạt.
Yes, I am here.
Okay, so the level structure of the IF, the enhance, please.
So there will be 3 pair of fluorine around. Yes, and 2 pair in the iode.
How do you know this one is another two more pair on the iodine atoms?
Because yeah, the iode because there is minus in the IF4 minus.
No.
So the total valence of electron in IF minus IF4 minus is 36 electron.
Sẽ đập 7. Cộng 7 nhân 4.
So total electron is 36, so 36 is the 2 is
18 pair. Yeah.
So this one surrounding fluorine atoms, there are 4, so 4 times 4 is 16, so
Yes.
you add 2 more electron pair on the iodines.
Yes.
Okay, you can see that this one, everything we learned from the previous class, and also I remind you that you have to learn in the fundamental chemistry one, please. This is why I don't want to spend time here anymore, okay?
Okay.
We will have this card not only for you, but also for all classes, for all class. Because this one is the required knowledge for the inorganic chemistries. This one also is a requirement to attend the inorganic chemistry is you must finish the fundamental chemistry 1 and 2. Okay, so now let's consider this one. What is the fifth of the? So now, how many electron pairs surrounding the iodine atoms?
6 pair.
How many electron pairs surrounding the iodine atoms?
6 electron pairs.
Okay, 6 electron pairs. 1, 2, 3, 4, 5, and 6.
Yes.
So please spend time to consider the classwork and also the homework and also read the textbook. Okay, I have already uploaded the textbook. Don't keep it until the final examination, please. And this one, please remember that this one is anion, okay? And you can see that I also make the response, the answer for the homework. I'm not so optimistic with this course. Okay, now with 6 electron pairs surrounding R, this one is a basic shape. So what is the basic shape for the number of electron with 6 electron pair? What is the basic shape for 6 electron pair?
Planner.
Check the table for the basic shape of 6 electron pair. What you can find from the tables, okay, it is
Octahedral.
so 8 electron pair is octahedral. This one is basic shape. The 6 electron pair now iodine in the center. So where is the lone pair? There are 2 lone pair here. So where is the 2 lone pair? The first lone pair you can keep anywhere you want. Maybe you can keep here. So where is the second lone pair?
It's below.
It's opposite
With the
with the first lone pair.
first one. Yes.
If, for example, you keep the lone pair here, you keep the lone pair here, so the another lone pair must be here. Okay, which means that opposite one.
Opposite one.
It's opposite electron pair. So the first you can keep anywhere. However, the second one must be opposite with the first one. And now this remaining position is for fluorine atoms. Okay. And what is the molecular shape of this one?
Square planner.
Yeah, okay, so in principle you can delete these positions immediately because there is no atoms. So now you can see here the molecular shape is a square planet.
Yes.
Okay, this one is square planet. Okay, so please remember this one. From molecular, draw the Lewis diagrams and then apply the VS-APR model to determine the molecular shape. Okay, so we finished this part. Now we can consider this next one. Okay, so let's finish this example for the VSEF theories. And now we move to the next. In this case, we will learn about the next point is the valence bond theories. And now we move to the theory to describe the bond formations. How the bond between the two atoms A and B form in the particular molecules. So here we describe the bond formations. So we can learn two theories, VB theory and MO theories. Okay. And now I think we have a short break before we can continue the next 2 points. Okay, so let's continue. The first one is about the. Now we can start the first theory is the valence bond theories. In the valence bond theory here, you can see that we say some of the principle for the theories. So according to the VB theories, the chemical bond is considered as the overlap of valence atomic orbitals on two different nuclei, so that both nuclei share a pair of electrons. Or in the short form, you can say that so the chemical bond in the VB theory is overlap of the atomic orbitals, and in this overlap there is or there are a pair of electrons, and you can apply this one when we consider, for example, where the most important, the most simple example is for the hydrogen atoms. So as you know, that's for the hydrogen atoms there is a bond between the two hydrogen atoms, and now we can describe this bond. So you know that so the hydrogen with the electron pair with the electronic configuration is 1s1. So it means that the one electron in the hydrogen atom is in the uh, s orbitals, in the s orbitals. And now when the two hydrogen atoms combine with each other, there will be a overlap between two 1s orbitals, and you can see in the overlap region here there are one pair of electrons. So in this case, we can describe the bond between two hydrogen atoms is the overlap of two 1s orbitals. So the overlap between 1s orbitals, and because here you can see that the electron density is along the axis, the intermolecular axis. So in this case, and the bond is called the sigma bond. So the sigma bond is the overlap or the electron density along to the intermolecular axis. The intermolecular axis is the line connect two atoms together. So this one is intermolecular axis. So it's for the hydrogen molecules. And we can consider another example is for the difluorine atoms. The first one we can consider the electronic configuration of fluorine with the atomic number of 9. So you can see that with the red color here, this one is valence electrons. In case of valence electron, when you draw in the square like this, you can see so 2s2, here's 2s2, and here is 2p5. And now in this pictures, I saw only p orbitals. I saw here only p orbitals. So there is a 3 p orbitals, and each p orbital is along to the each axis of the coordinated system, along to x-axis, y-axis, and z-axis. Yes. So we can say it's 2px, 2py, and 2pz. So first of all, we can see here because of fluorine, there is one unpaired electrons here in the two p orbitals. So it means that now the two fluorine atoms, it means that the two fluorine atoms can overlap each other to create the bond between the fluorine atom, between two fluorine atoms by the combination of two lone pair, of two unpaired electrons. So here's in this picture, you can see one fluorine has one unpaired electrons, and another unpaired electron is formed another fluorine atoms, and now the overlap between two p orbitals here form the sigma bond between fluorine and fluorine atoms. It's easy to understand here because you can see that now the overlap here is between the two p orbitals along to the intermolecular axis. So in this case, this one is also sigma bond. So now we can describe some of the bond ring formation in fluorine molecular is the overlap between two p orbitals with unpaired electrons of two fluorine atoms. Okay, you can see here this one is fluorine atoms, a sigma bond. Okay, It's easy to describe here. So here you remember that we describe the chemical bond as the overlap of atomic orbitals. So first of all, you should determine, okay, so the free electrons belong to which orbitals, and then you can use this orbital to uh, produce the chemical bonds. In case of hydrogen, the single bond, the electron is belong to the 1s orbitals. However, in case of fluorine, so the unpaired electron is belong to the 2p orbitals. So in this case, for hydrogen, we use overlap 2s orbitals. However, for the fluorine, we use 2p orbitals. And if you consider the more complicated example, for example, for dioxygen, yes. For the dioxygen, so here is the Lewis structures of each oxygen atom. You can see one. So each oxygen atom has two unpaired electrons. So now we can understand when we combine two oxygen together. So this when you compare this one, so you can see that when you compare what will happen here. So this one combined with this one, and this one combined with this one. Okay, so first of all, you can see there is one overlap between two p orbitals. Okay, this one, and this form the sigma bond. This one is two p orbitals. So you can see here, first of all, is a three p orbitals. So two of them is with one
Không nghe thấy, con
electron.
đeo tai nghe.
Two of them is with one electron. This one is the first one, and this one is the second one. And also for another oxygen, the first one and the second one here. And now you can see that one overlap between the two p orbital is produce a sigma bond. And because the p orbitals is perpendicular with each other, so and this one you can see now they can overlap. However, this with this kind of overlaps, so the electron density is not along to the intermolecular axis. This one is in the two sides of the intermolecular axis, and this chemical is a pi bond. So for the dioxygen, there is one sigma bond between formed by the overlap of two pz orbitals, and another pi bond is formed by the overlap between two pi x or two pi y orbitals. Okay, so in oxygen is one sigma bond and one pi bond, Okay, you understand these pictures. And consider another example is for the nitrogen is with the electronic structures like this. So here with the nitrogen, there are three unpaired electrons, each of them located on the uh, p orbitals. So here picture, so 1, 2, 3. So nitrogen has three p electrons with each of them has one unpaired electrons. And now when you combine two nitrogen together, this one, okay, you can see they couple with each other. And now the first one is also the sigma overlap or sigma bond formation. And for the remaining two p electron which perpendicular with the pi z orbitals here, so they can overlap to produce two pi orbitals. Two pi bonds. So here's between the nitrogen there's a triple bond. So one of them is the sigma bond, and the remaining two bond are pi bonds. Here you can see here, so the overlap. The first pair p orbital is produce a pi bond here, and another overlap is from the second pi bond. Okay, this one. This one is for the VB theory applied for the homonuclear diatomic molecules. And now we can consider one another example. For example, now we can use VB theory to describe the bond formation in the CO, in the carbon monoxide, in the carbon monoxide molecules. So let's consider these examples. Now use VB theory to describe the bond formation in the CO molecules. The question now is to consider VB theory for CO, for carbon monoxide. Okay, let's prepare in few minutes and I will ask one of you.
Mày thích mày sau một phút.
Okay, so for this example, first of all, we consider the atomic structures of carbon and for atomic structure of carbon and oxygen.
Sao quá?
Phùng Thị Nương.
Dạ em đây ạ.
Atomic structures of carbon and oxygen, please.
Thì sẽ xích ạ.
So let's consider the
Bây giờ ai được đi?
valence electrons of carbon.
Carbon E
444.
Okay, so this one is a molecule. This one is atomic structure of carbon. It's atomic structure of carbon. Now we consider only the valence electrons of carbon. And also this one is for the oxygen.
oxygen OZ bằng 8.
This one is 2p4. And now let's consider the valence electrons on these. We don't need to care for the remaining ones. The first one will be 2s2 and 2p2. Okay. And do everything like we have already see on the lecture notes. Step by step at the beginning, and then we can speed up. 2p2 and 2p4. Okay, now this will be returned here. When and for oxygen, okay, so now this one is atomic structure of carbon and oxygen, and so now which orbital overlap with each orbital to form the bond in CO. Okay, now let's start from these atomic structures. And be careful with that. So the atom overlap each other to form the more stable state with 8 electrons in the outer shell. This one has already learned in the previous class. So now let's see so which orbital will overlap each orbitals. No.
Như thầy là hai orbital pi, cái mà có hai mũi tên ấy, của
Đã gọi là orbital thì gọi là orbital p đi đúng không ạ? Còn
dạ vâng ạ.
p orbital thì là p orbital is small. Vậy cái nào thay của cái nào? Which one overlap each one?
Cái ô đầu tiên của orbital B, của orbital pi, của cái carbon ấy ạ, sẽ liên kết với cả cái ô thứ hai của oxy ạ.
Okay, let's take a look. Okay, here so another. Yeah, so the first one maybe let's see here. So now the carbon has two unpaired electrons, and the oxygen also has two unpaired electrons. So here we have the overlap. The first one between these two orbitals, and this one also. Okay, so now is there anything else? No. Let's make this type symbol for the overlap between P and P. P orbital, this P orbital, and this P orbital, this P orbital, and this P orbital. So is there another overlap?
Cái này phải đổi chiều ấy ạ.
Okay, we can consider this one later. So is there another one? What is this one? Or is there another overlap between orbitals? Is there anything else? Yes? Hmm?
Dạ không có. Hai cái ở dưới của oxy nó sẽ liên kết với cả hai cái trên của carbon ấy ạ, thì nó sẽ ngược chiều nhau để liên kết với nhau ấy.
Okay, this one we can consider later. So is there any another kind of overlap, or only this one is enough? Is there anything else? Not only the spin of electrons.
Em nghĩ là đủ rồi ạ.
Okay, so now how many electrons in the valence of carbon?
Và cả cái ô trống thì cái ô trống của carbon ấy ạ sẽ liên kết với cả cái ô ở dưới luôn ạ.
Why? Why we must consider this kind of overlap?
Bởi vì là nó chưa đủ 8 electron ở lớp
Okay, so how many electrons carbon has now? Let's consider on the screen now. I draw only two.
4.
Yes, first one overlap with this one, and this one overlap with another one. Okay, so now how many electrons in the valence of carbon? When we consider only two of this type two overlap, we consider only two overlaps.
Bây giờ carbon thì chỉ có 4 e lớp ngoài cùng.
No, it's wrong question. It's wrong answers. Consider also the overlap between the two p orbitals. So now how many carbon electrons carbon has now?
Tất cả thì là có 6 ạ.
Okay, so now only six. 1, 2, 3, 4, 5, 6. Because so now they overlap each other. So this one can count the 4 carbon. And now how many oxygen has already has? So how many electrons in the valence shell of oxygen now?
Oxy là đủ 8 rồi ạ.
Okay. 1, 2, 3, 4, 5, 6, 7, 8. Please be careful how can we count the number of electrons, okay? Please remember this one. Okay, now you consider this type of overlap. So it means that the oxygen has 8 electrons, however, carbon has only 6 electrons. This one we must consider the another overlap. This one is a very special one. It's different from the previous overlap. What is the difference here, Neil? What is the difference between the green one and the red one now?
Cái gì vậy?
Ờ,
Ở đâu?
And between the blue one and the red one? So what is the difference between this type of overlaps?
như thế là cái liên kết nó sẽ khác nhau ạ.
What is the difference? In detail, please.
Liên kết của cái xanh và liên kết của cái đỏ nó sẽ có sự khác nhau ạ.
What is the difference?
Ờ, của cái liên kết thầy khoanh màu đỏ sẽ là liên kết cộng hòa trị.
And what is the difference? And what is the name for the green for the blue one?
Cộng hòa trị là covalent ạ.
The green one is covalent bond, and the red one is the.
Còn là cái của liên kết xanh là liên kết
So this one is covalent bond. What is for the blue one? Okay, so in this case you can see that okay, thank you very much. Okay, and I should explain here. You can see that the carbon atom has two lone pair here. Sorry, two unpaired electrons here, and the same for oxygen. It has two lone pair here, so each of them can overlap each others. And after consider this type of right overlap, you can see that oxygen has 8 electrons in the valence shell, while in case carbon only 6 electrons. Is why we must consider also the blue one here. And when you count the blue one, you can count for carbon is 1, 2, 3, 4, 5, 6, 7, and 8. And for oxygen is the same 8 electron 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so and now we can specify the difference between the green one and the red one, and the blue one and the red one. You can see that for the red ones, so each one from carbon, one from oxygen. However, for the green one, both electron is from oxygen. This one is the difference. Okay, it's very clear from the shape. Yes. So for the red one, one from oxygen, one from carbon. However, for the blue one is 1, 2, and both electron is belong to the oxygen atoms. And the red one is covalent bond, and another one is also in principle. This is also the covalent bond. However, they call it another name is coordinated bond. Or coordinated bond. Okay, coordinated bond. In this case, we can say that the oxygen donates the electron pair to the empty orbital of carbon. And now we can describe this one in the orbital shape. Let's consider the first one, carbon and oxygen. Okay, so this one you can see how would you are at the fundamental chemistry one. Seems learning by English as your knowledge is not so good. And this one is not the first time I complain for the advanced programs. It's not the first time. However, it seems it doesn't change after the semesters. I don't understand. Because you pay more your French with the standard program. However, the quality is not more than the standard product. It's really programs. You pay more, however, the quality is lower. It's not really nice. Carbon and oxygen. If your English good or if you spend more time to reading the textbook, your knowledge will be better. First one, let's consider the overlap between the first p orbitals. Okay, always they produce this one, this one. Let's consider here. This one is p orbitals. What? Okay, and maybe I think that we should delete the carbon here. Maybe this one, I don't know. Let me delete by this one. Okay, so the first one here, maybe we can mention this one is a carbon, and this one is extend this one a little bit. Okay, it's more to draw the name of the item here is carbon. Carbon on the left hand and oxygen on the right hand. Okay, but first overlap between carbon and oxygen, and each for example here, each atom has one lone pair, one unpaired electrons. It's why they can overlap each other. First one here is we produce a sigma bond. Okay, now let's consider another pi orbitals. Okay, it's a little bit small. It's sigma bond, and now we can consider this one again. And let's rotate this one 90 degrees. Okay, and now the second p orbitals. Please understand what I'm drawing. Okay, this one is p orbitals. Let's keep it here. It's more better. Okay, and now for oxygen, it's one unpaired electrons here, and also for carbon, there's another unpaired electrons. We should draw this one in the red color. Oh, no, not so nice. First one is red color, second one also red color. Why is red color? Because it draws red color here. This one red color, red colors. Maybe this one keep the red color. It's easy for you to understand. Okay, what's happening? Another one is a red color, so you can see now what does it mean, the sigma bond and also the pi bond here in this situation. This one is the pi bond. Now this one is one sigma and one pi bond. Okay, from the overlap between the two items. Okay, maybe this one is better. Good. And also maybe things. So we can see that one overlap is sigma, and another overlap is pi bond, and now we consider the remaining p electrons. Okay, the remaining p electrons here. You should draw like this, or maybe you can reduce the size a little bit for you to understand. Oh, no, it's not so much. Okay. And another one also from oxygen. Also from oxygen, yes. And please remember that for oxygen now, the carbon, this one is empty origin, so I don't draw any arrow here for this orbital carbon. However, for oxygen, as you can see that for oxygen there's one p electrons with pair of electron pairs, is why. Okay, so this one is for oxygen. Okay, and Now if you consider another one, you can see that okay, this one is another, maybe this one is a green one, okay, this one is a red one. It's a red one, so I think this one is being more become more clear for you to understand. Yes. Okay, so the between this one is the green one is another the second pyrogens, and now we can draw the bond between carbon and oxygen like this one. Okay, there is a triple bond between the carbon and oxygen, and if you consider here is one lone pair and also one lone pair in carbon. Yeah, so this one is the liquid structures for CO2, and also this one is describe the bond formation in the CO molecules. Okay, so now we can apply this theory for to describe the bond formation in another molecules. For example, now we can consider the water molecules. Yes. And we can use the same strategies for to describe the bond formation in water, like for CO. However, the water is much more synchronous than for CO. Here we can see that the hydrogen has only one electron in the outer shell, so hydrogen is that one. So atomic number is one, so it's only one S1. Okay, and for hydrogen here we can draw only the shape for the S orbiting here, so only one electron. You can see here. What? And for oxygen is the same, so we can keep this one is maybe we can change this one to the black colors, and this one for the red color, this one also for red colors. And now what will happen when we reform the formation between the hydrogen and oxygen? And I think that you have already know that. So we will have this kind of formula for water. So each of oxygen bond with two hydrogens like this. And now we can describe the bond formation in water. So it's very clear like here, so we can draw the s orbitals of hydrogen here. From here we can shift to here, you can see, okay, what is really the overlap here. So this one is each s orbital of hydrogen, and this one is over as a hydrogen oxygen. So it now here's hydrogen. Okay, this one is for hydrogen, and this one also for hydrogen. And this one combine this one or the two p orbitals of oxygen overlap with s orbital from hydrogen, they can form the OH bond here. Okay, the OH it form S is from the s orbitals of hydrogen and p orbital of oxygen. And now we can draw the pictures. So let's consider the p orbital of oxygen. So as we know that the two p orbital is perpendicular with each other, so we can draw like this. This one is for oxygen, and for another one for another oxygen. Let's rotate this one. Okay. Now we have a, this one is p orbitals of oxygen, and now they overlap with s orbital from hydrogen. S orbitals. Okay. Yeah, this one. Shift a little bit here for the oxygen. Okay, this one for hydrogen. S and S orbital here. So this one is a picture in the water molecules. You can see this one. The first one is draw the p orbital of oxygen, and another the cycle here is s orbital for hydrogen. This one is not so difficult for you to understand. However, I will give you one question. In this situation, let's see. Okay, so in the center here is oxygen, and another one is hydrogens. This one is oxygen, and another one here is hydrogens. Okay, let's draw the here. It's from one from hydrogens, another one is from oxygens. Okay, so another one is also for hydrogens, and another one here is for oxygen. However, it should be managed for me. Rotate this one a little bit. Okay, good. And now we see it for, it should be in overlap. Sorry, I draw a little bit mistake here. This one should be in the overlap between the two items. So easy. Okay, so it's from the bond like this. Okay, good. And the problem here, you can see that now what is the angle between the hydrogen and oxygen? Please determine the angle here. HOH, what is the angle?
109 108.9 208
Mạnh Dũng. What is the angle between the two bonds? Or you can determine the angle HOH here in this situation. What is the number of the angle here? How many degrees? Mr. Mạnh Dũng is not here. Okay, what another person? Đức Văn, Hoàng Văn Đức. Diệu Anh.
Teacher, here.
What are you doing? What is the angle HOH now? From this picture, what is the angle between the hydrogen, oxygen, and hydrogen?
The HOS is 90
90 degrees. Because you can see that the two pyrogen is perpendicular with each other, so the angle is 90 degrees. However, from the experiment, they say that the HOS is not 90 degrees. From the experiment, we know that this angle is about 105 or 106. I don't remember the exact values. However, it's not 90 degrees. This one is about 105 or 106 degrees. This one is from experiment, and this one is from the theory. So the problem here is the VB theory cannot understand why this one is 105 degrees, because according to the VB theory, the angle here is 90 degrees. Actually, because the difference between the real values and also the expected values here, so it's why we cannot use the VB theory to describe for the molecular with more than 3 atoms. And if you want to use the VB theory to describe the bond formation for the molecular with more than 2 atoms, you must use the VB theory and the hybridization scheme. So please remember that this one is 90 degrees. However, the angle here is 105 degrees. So we cannot explain why. So the VB theory cannot be used to describe the bond angle in the water. So here you must apply not only the VB theory, you must also the VB theory and the hybridization scheme. Hybridization scheme. Okay. But please be careful because we use the VB theory and hybridization scheme most in the describe the bond formation in the organic compounds. Okay. I just mentioned you this time, and in next one in the lecture you can see that we don't go detail in describe anymore. Okay. What does it mean? Okay, so let's stop here a little bit, and we can come back to the point here. This one is what I mentioned is for the polyatomic orbitons. Yes, for the polyatomic orbitons, we must use the hybridization of the atomic orbitons. So the hybridization of the atomic orbitons. The hybridization of atomic orbitons is a combination of atomic orbitons to obtain the new orbitons for the molecular shape in terms of sigma bonds. And remember that this one is only the mathematical method. It's not the reality what happened inside the atoms. This one is they introduce this they make the image. Okay, so let's see that the atomic mix together to bond the new atomic orbitons. However, in reality, there's not kind of mixings. This is why I mentioned it's only the mathematically obtains. It's not the realities. And now the number of hybridization is equal to the number of atomic orbital mix. The type hybridization varying with the type of atomic orbital mix, and the label of hybrid orbitals reflects the contributing of the atomic orbitals. Okay, let's keep this one in mind because we will consider these examples.
Yeah.
Okay, so let's come back to the water molecule. Here's how we can use the hybridization scheme to describe the bond in the water molecules. Okay, now let's consider the water molecule here. Now it's a related question now. Okay, this one is related to the molecular shape of the molecule here, of the water here. So you can count from the Lewis structure of the hydro of the water here. What is the, we can see from the structure of the water molecules. Let's move it a little bit to here. Here, this one is for waters. So in case of water molecules, because you can count the number of electron pairs surrounding the oxygen here, 1, 2, 3, and 4. So there are 4 electrons surrounding the oxygen atoms. When you consider the molecular shape of the oxygen, you can draw like this here. So oxygen with 4 electron pairs. Okay. And then there are 2 positions is hydrogen, and another position is for the lone pair. For example, here this one is for the lone pair. So it means that now surrounding oxygen there are 4 pair of electrons, and let's assume that though this 4 electron pair is equal, or this 4 electron pair is equal. So we can make the mix between the 1s orbitals, 1s orbitals, and when we mix with 3p orbitals. Why we mix 1 and 3? Because here you can see that surrounding oxygen there are 1, 2, 3, and 4. So we need 4 equal electrons, or 4 equal orbitals. Okay, 4 equal orbitals. 1s and 3p orbitals. So 1 and 3 is 4. This one. So because 1 plus 3 is 4, so you start from 1s orbitals, atomic orbitals, and 3p atomic orbitals. So 1, at first let's consider 1 and 3 is 4. So the first number is 4, okay? And how many atomic orbitals? So 4 atomic orbitals. First one is the number of the hybrid atomic orbital is equal to the number of the initial atomic orbitals. 1 and 3 is 4. Okay, and then what is the symbol for the hybrid atomic orbitals? 1s and 3p. It means that 1s, 3p, so sp3. Okay, the name is depend on the type of and the number of the atomic orbital used. You use 1s and 3p, so it's sp3. Okay. As I remember from the last year, okay, the last year is very funny. In the examination, okay, I asked, okay, what is the hybridization scheme of these molecules, of these oxygen atoms? Okay, I know that they use handies to check the information from the internet, and they find, okay, the answer is sp3. However, they change from sp3 to Vietnamese. Do you know what does it mean? SP is sản phẩm, and sp3 is sản phẩm 3, and sp2 is sản phẩm 2. Okay, this way how you can learn this one. Okay, I really I don't know what could say in this situation. Mhm. You use a document, you use any electronic device, how you don't understand what you are feeling, what you can find from the internet without any ideas. Mhm. It's very funny and also crazy, man. So let's start from 1s. In here, when you consider the occurrence, so we can say, okay, so 1, 2s orbitals and 3, 2p orbitals. Okay, be careful, it's not 20, 12 or 32, okay, it's 1, 2s orbitals and 3, 2p orbitals. And they form 4sp3 orbitals, okay. 1 and 3 is 4. 1s and 3p is sp3. This one is hybridization scheme you use for oxygen in this situation. Mhm. Okay, so this one, let's consider the structures of oxygen here. First, you have 1 and 3p. Mhm. I know that for all of you, or for some of you, this one is new, or some of you don't understand anything. However, spend time at home for this. This I always advise for the student. Spend more time to learn, or do something is useful for you for your futures. Don't spend time for watching TV or something else, because after 4 years in universities, you don't have any time for learn anything. Okay, after you finish or after you graduated, you will spend time for the job to earn the money, and this time there's no time for learning anything. And you can have a wish, okay, so maybe it's better and we can use the time when we learn in the universities. However, you cannot come back anymore. Okay, this one is very important. Make your life more useful and more meaningful. Okay, so when you mix here, you can see when you mix 1s and 3p here, you form, yes, you can form 4 equal atomic orbitals. Okay, this one is formed by combination of this one, and also with here's 1s and 3p, crazy things. I hate you. Okay, this one is 1s and 3p is sp3. And now for oxygen, now oxygen has 4 equal atomic orbitals, and 2 of them has a lone pair here. Okay, and another 2 of them has unpaired electrons, and this one can overlap with atomic orbitals for hydrogens. And because here you know the angle is the standard angle here is 109 degrees, so this one is somehow is near to 105, more than 90 degrees. So here's for the hybridization scheme of oxygen is sp3. Okay, this one is hybridization scheme. Okay, now we can come back the example for the here for the molecular shape. Maybe you can determine the hybridization scheme for the central atom here. For example, we can determine a hybridization scheme for the carbon, for the nitrogen, for the sulfurs, and also for the iodine. Okay, so what is the hybridization scheme for the central atom with the red color here? tiến mạnh. Ngọc Minh. Ngọc Minh. Đức Anh. Quang Anh. Diệu Anh. Văn Đức. Thu Dung.
Dạ em có ạ.
So let's please consider the hybridization scheme for the red items in the form molecules.
Ammonia
Sorry.
ở cái NH3.
Yes, with this one, let's consider with the first one is CH4 and then NH3, SF4 and IF4 here. Okay, so first let's start with the CH4.
Dạ vâng ạ.
What is the hybridization scheme for CH4?
SP3.
What is? Sorry,
SP3.
S?
SP3.
Okay, SP3. Why do you choose SP3?
Dạ.
Why do you choose SP3, not SP2 or SP?
Vì ở đây có 4 liên kết ạ.
Okay, good. Next one, NH3. First one and the second one.
SP3 ạ.
Here, if you draw on this one is incorrect one. However, if you draw like this, it's SP2. Okay. However, for the correct one, what is a hybridization scheme?
SP3 ạ.
SP.
SP3.
Okay, SP. Next one, SF4.
DSP3.
No, it's not the SP3. SP
3D.
3D. Why do you choose this one? Quickly explain later for your friend, not for me.
Tại vì nó có 4 liên kết và một E kết đôi ạ.
It's not so clear. Let's try to explain for your friend, not for me.
Tại vì nó có một cặp E liên kết, có bốn liên kết và có một cặp E không liên kết ạ.
It's not so clear. You understand?
Nó có 5.
Yes, okay. Let's keep continue.
Thì nó có 5 electron pair ạ.
Okay, so okay. Then so why do we choose sp3d? Okay, 5 electron pair, and why you choose sp3d?
Dạ, tại vì nó liên kết cả ở lớp D ạ.
No. Your friend don't understand. I'm sure. Okay, now you can see 5 electron pair. So S is 1, P is 3, 1 and 3 is 4. Now if you need 5 electron pair, so 1s, 3p and 1d. 1 and 3 and 1 is 5. Okay?
Vâng ạ.
Okay, this one is you can explain in this case is for your friend to understand. Because this one is very important. Sometimes you don't need to understand what I mean in SP3D. However, you can determine the hybridization scheme. Okay. Okay, for the next one, what is the hybridization scheme for the last one, for the IF4?
Em chưa làm được câu vậy ạ.
Okay, let's count together with me. How many electron pair here?
6.
Okay, so what is the hybridization scheme? Keep on to me. 6, 1, 3, and
D2.
Letting around. Okay, so you teach your, for example, your nephew something like this. Okay, so 1 and 3 is 4, and 4 plus x is 6. So what is x? 6x. So it should be 1 and 3 and 4. So 4 and 2 is 6. So now it's SB 3
Two.
and 2. Okay,
Two.
it's very important and very simple. Okay, 1 and 3 is 4, 4 and 2 is 6. Okay, so finish. Don't need to have any idea about what is a hybridization scheme. Okay, we just have questions. Don't have any idea. Okay, however we can finish the questions. This one is very important. However, you need to draw the Lewis structures. You can see that how important the Lewis structure is. That's why I must remind you about this one. Okay, now it's time to the MO theory, and we must finish this topic today. If you cannot finish topic today, you can read the last part in the textbook, and you can learn by yourself. Okay, because this one is only the repeat, not the new knowledge. Okay, so let's consider the next one. So for the teaching online, for the online course, it means that both a teacher and a student must work more, not like for the offline course. If you should have this, if you want to be sure that the quality of the course. And this is also the question, so please change the way of the learning. Self-study is very important. This one is not the second year in the university, it's not the first years. And it could not behavior like in the high school. Okay, in the university, there is no new knowledge. It's very similar when you finish your university, when you go for a job. You cannot say, okay, this one new for me and I could not finish this one. Okay. If your boss asks, okay, so please finish this one, you cannot say, oh my God, it's new for me. I cannot say, you can ask for another person. Okay, maybe 1 time and 2 times is okay. However, for the 3 times, I think that you should change to another software. It's the realities. Okay, so the MO theories, the molecular origin theories. What do you mean the MOs? So the first one, I think that you should understand what is one is a general. This one is very similar with the atomic origins. You simply change from the atomic to the molecular. As finished, as one is you can understand. And the first question is how good you understand the concept of atomic origins. If you really understand what is atomic origins, so you can simply replace the atomic by the molecular. So this one is okay. For example, let's consider here the atomic origin is a space surrounding the nucleus in which a single electron can occupy. And now you can extend this one for the molecular origins. The molecular origin is space spread out the molecules. Okay, so all the space surrounding the molecules. So here, in case of atomic origin, is space surrounding the nucleus. However, here is space surrounding the molecules. And in